All right, so our book doesn't specifically throw in a section on this, but it does show up on my tests and on the central test. So we're calling this lesson 3.5. What you're going to learn about here is integration by trigonometric substitution. Or, as I like to call it, kind of looks like someone was doing the Pythagorean theorem. We'll see what we are talking about there as we look at our first example. Okay. So this one, the reason why it looks like somebody was maybe doing the Pythagorean theorem is because I see the square root of x squared minus 25. Okay? And that looks like the kind of problem where maybe I had an a squared plus b squared equals c squared, and maybe I tried to solve for the b, and so it said b squared is c squared minus a squared, and so b would be plus or minus the square root of c squared minus a squared, and this part in particular resembles what's going on there. Okay? So that's why I say it looks like someone was doing the Pythagorean theorem. Okay? So getting that out of the way, the question then is, what did the triangle look like that they were doing this Pythagorean theorem to? So I'm going to draw a right triangle. Okay. And if that was the case, the way that we had that example in there before, it was c squared minus, for example, the a squared. Well, c is always the hypotenuse, so what they must have seen was a right triangle where x was on the hypotenuse, and then one of the legs was 5. Because if I do the Pythagorean theorem to that, then this leg, by calculation, is the square root of x squared minus 25. We keep the positive version of that because this is in a right triangle. We're talking about lengths of sides here. So this must be the triangle, and I can pick any one of these angles to talk about here. And what I'm going to do is I'm going to reframe this indefinite integral as a trigonometry integral. Okay. So this 1 over the square root of x squared minus 25 looks an awful lot like opposite over adjacent for what I have here. So I could definitely write that the tangent of my theta is 5 over the square root of x squared minus 25, and dividing both sides by 5, I can say that 1/5 tangent theta is 1 over the square root of x squared minus 25. And so I could make that substitution here. I could say I've got the 1/5, that's a constant, I can kick it out in front. The 1 over the square root of x squared minus 25 is just tangent theta. And then I still have this dx. Okay? Well, tangent theta and dx, my variables are not in agreement here. So I need to, since I made the effort to change the 1x into thetas, then I need to do that with the dx as well. So if I look here, what I'm looking for is the easiest possible way to create a dx, which would have an x in the numerator and a number in the denominator. And so that looks like hypotenuse divided by opposite. That is a cosecant, hypotenuse over opposite. So I can say that the cosecant of theta is equal to x over 5. And so 5 cosecants of theta are equal to x. And if I take a derivative on both sides, I'm going to get a negative 5 cosecant theta cotangent theta d theta is equal to dx. So I can put that into my problem now. So I've got 1/5. I have the antiderivative of the tangent theta. That was the part that I substituted for all of this. My dx now is a negative 5, so I'll kick the negative 5 out here, multiply that in there, and I have a cosecant theta, cotangent theta, d theta. Okay, so all of that stuff in red is now my dx. which looks significantly more complicated, but if I do a little bit of simplifying, this obviously just becomes a -1 out in front, and a tangent, and tangent is sine over cosine, and cotangent is cosine over sine. The tangent times the cotangent, those cancel each other out, and I'm just left with a cosecant theta d theta. Okay. This is one of the formulas that we provided you with. So the antiderivative of cosecant, we'll show you the development of that in a separate video. Okay. But it says that this will be, so the negative that's out in front, and the formula for the cosecant, or the antiderivative of the cosecant, is negative natural log of the absolute value of cosecant theta plus cotangent theta, plus a constant. Right? All right, but this is all in terms of theta. Certainly my negative and that are going to cancel each other out. The natural log's not going anywhere, but my cosecant of theta is the same thing as x over 5. So this is the natural log of the absolute value of x over 5 plus the cotangent, which would just be the tangent flipped over. So that is a square root of x squared minus 25 over 5 plus a constant. Okay. This worksheet will usually go a little bit farther than this. If you're curious as to, if you stopped here, why the book has a different answer when you look it up, it's for this reason. We have a common denominator in here already. So that's an x plus a square root of x squared minus 25 all over 5. But that is division inside a logarithm, which I can rewrite as subtraction. So x plus the square root of x squared minus 25 minus the natural log of the absolute value of 5 plus a constant, but a constant minus a constant is still just a constant. So we will see natural log of the absolute value of x plus the square root of x squared minus 25, and we'll absorb that all into just a single constant and write our answer that way. Okay, so this is the thing that you take the derivative of in order to get 1 over the square root of x squared minus 25. All right, next example. I said this was a little twistier. It may not look that way from the beginning, but again, it does look like somebody was maybe trying to do the Pythagorean theorem. We see that there's addition inside here instead of subtraction, so these must have been the two legs, and I was trying to find the hypotenuse. So, and I have choice on my legs here. I'm going to make one of the legs x, and one of the legs 7. And then this would have been the square root of x squared plus 7 squared when I was trying to find that. Now, it doesn't matter which one I call x and which one I call 7, and it doesn't matter where I put the theta. It will change maybe during my substitutions what the answer looks like, but it won't change the final result. All right, so I want something to substitute for the square root of x squared plus 49. So hypotenuse over adjacent, the secant of theta, is equal to the square root of x squared plus 49 over 7. So 7 times the secant of theta is the square root of x squared plus 49. And I can make that substitution in there. So this becomes 7 times the integral of secant theta dx. Again, I don't have agreement in my variables, so I need to go find a dx. The easiest dx I can possibly find is to put x in the numerator and a number in the denominator, so that looks like opposite over adjacent, that's tangent. So tangent theta is x over 7, so 7 times the tangent of theta is x. And so taking derivatives on both sides, 7 secant squared theta d theta is equal to dx. And so now my problem looks like 7 and the secant theta. I have the integral of, and my dx here in green is another 7 out in front, and a secant squared theta d theta. So that all simplifies now to 49 times the indefinite integral of secant cubed theta d theta. Well, that's a power of an exponential or of a trig function. So that requires a reduction formula. If I look up my reduction formula for secant, so I've got the 49 here, and the reduction formula says 1 over n minus 1, so that's going to give me a 1/2 secant to the n minus 2. So that's going to be a secant theta, tangent theta, plus n minus 2, which is a 1, 3 minus 1 over, or 3 minus 2 over 3 minus 1, times the integral of secant to the n minus 2, so this is going to be of a secant theta d theta, which I also have a formula for. So far this is looking like a 49 halves secant theta tangent theta plus 49 halves times the antiderivative of the secant, which according to my reduction formula is the natural log of the absolute value of secant theta plus tangent theta. Plus a constant. So I don't want to scroll that up too far because I want to be able to see my triangle. I need secants and tangents. I can see where I've already written secants and tangents here. So this is a 49 halves. Secant theta is also known as the square root of x squared plus 49 over 7 times the tangent theta, which is x over 7, plus 49 halves times the natural log of the absolute value of the square root of x squared plus 49 over 7 plus x over 7 based plus a constant. So doing some simplifying here, I have a 49, I've got 7 divided by 7 there. It looks like I have a 1/2 x times the square root of x squared plus 49 plus 49 halves times the natural log of the absolute value of x plus the square root of x squared plus 49. Again, like the last example, I'll write it all over 7. Split it into subtraction, the minus 49 halves times the natural log of the absolute value of 7, I will just absorb into the constant, and this is my answer for the antiderivative of the square root of x squared plus 49. Let's keep rolling with some examples. All right, square root of 9x squared minus 1. So the setup here, again, slightly differently. Maybe not significantly. It looked like the hypotenuse is the 9x squared part here. So I did hypotenuse squared minus 1 of the leg squared. So if my hypotenuse was 3x and one of these sides was 1, then this would be the square root of 9x squared minus 1. And I can pick the theta to be anywhere that I want. I have a 20-year rut of drawing it exactly that way, so, but it's not required that we draw it that way. In this case, it looks like the way that I've drawn it, that I'm going to have a cotangent. Oh, I'm using different colors for that. I'll try to be consistent there. So the cotangent of theta is the adjacent over the opposite, so that's my 9x squared minus 1. Don't need any changes to that. So this is indefinite integral of cotangent theta dx. And my variables don't agree. The easiest way to make that substitution is going to put the 3x in the numerator, or the 1 in the denominator, so that looks like a hypotenuse over opposite, which is cosecant. So the cosecant of theta is going to equal just 3x, so 1/3 cosecant theta is equal to x, so negative 1/3 cosecant theta cotangent theta, taking d theta, writing the differentials here will give me that for my dx. So I'll kick the negative 1/3 out in front, and I'm going to have a, I've got my cotangent theta, and a cosecant theta cotangent theta d theta. All right, well, what's this going to look like then? I've got a negative 1/3, and it looks like a cotangent squared theta cosecant theta d theta. If I think about what I've got going on there, I know that the derivative of cosecant is cosecant cotangent, but I don't have extras of those. I know the derivative of cotangent is cosecant squared. That's not really getting me anywhere either. I believe I could write this all in terms of powers of cosecant, because where there's a cotangent squared, it can be rewritten as a cosecant squared. So my Pythagorean identity, sine squared theta plus cosine squared theta is equal to 1. If I want a cotangent out of that, I'm going to divide everything that's cosine over sine. So if I divide everything by sine squared theta, I'm going to get a 1 plus cotangent squared theta is equal to cosecant squared theta. So I can replace a cotangent squared theta with a cosecant squared theta minus 1. So I'll rewrite this as negative 1/3, and my derivative of cosecant, if I can spell it correctly, cosecant squared theta minus 1 times cosecant theta d theta. I'll definitely be extending some page here. This is now going to become two different problems. I've got a negative 1/3, it's the antiderivative of cosecant cubed theta d theta, plus 1/3 antiderivative of cosecant theta d theta. This first part, I'm going to need a reduction formula for that. So going to my reduction formula, I'm going to get negative 1/3 for cosecant to the nth power says I should have a negative 1 over n minus 1, so that's going to be a negative 1/2. Cosecant theta cotangent theta plus 3 minus 2 is 1, 3 minus 1 is 2 times the integral of cosecant theta d theta. And then I still have this plus 1/3 of cosecant theta d theta up here. So if I do a little distributive property, I'm going to have a 1/6 cosecant theta cotangent theta minus 1/6 antiderivative of cosecant theta d theta plus 1/3 antiderivative of cosecant theta d theta. And these are like terms. I could throw those things together and then only do the cosecant formula once. So this is a 1/6 cosecant theta cotangent theta. This is 2/6 minus 1/6 leaves me plus 1/6 antiderivative of cosecant theta d theta. And looking that formula up, that's going to be a 1/6 cosecant theta cotangent theta minus, I believe the antiderivative of cosecant is negative natural log, so negative 1/6 natural log of the absolute value of cosecant theta plus cotangent theta. Plus a constant. So I need to know what cosecant and cotangent were. Cosecant is 3x, cotangent is square root of 9x squared minus 1. That's my first term minus 1/6 times the natural log of the absolute value of 3x plus the square root of 9x squared minus 1 plus a constant, and a little bit of simplifying here. This is 1/2 x times the square root of 9x squared minus 1 minus 1/6 times the natural log, absolute value of 3x plus the square root of 9x squared minus 1 plus a constant, and that is my final answer. Okay, a lot of steps, but this maybe more than anything else is sort of formulaic in the approaches that we take. There are some twisty things that can be done beyond that we'll take a look at probably in a supplemental video to this one.